Okay, welcome back Science 10s to our next lesson in chemistry, and today we're going to be talking about acids and bases. Hydrogen is weird. He's a weird element because if we look on the periodic table and we determine the number of protons, there's only one proton and there's only one electron. The other thing is that in the first shell, there only fits 2 electrons. So it's kind of equal for him to give one away or to take one. So he has a hard time really knowing what he is. If hydrogen comes near a carbon, he's very happy to go over to the carbon and share his electron, and 4 other hydrogens do that to make CH4. But yet if he interacts with something like chlorine, he's very happy to give away his electron so that he becomes a plus and the Cl becomes a minus. Now when hydrogen gives away its electron to a nonmetal like chlorine and then it goes into water, it dissociates or breaks apart into its ions just like an ionic does. So if it goes into water, it's going to dissolve and get broken into its H plus and Cl minus ions. Now this guy is even more weird because remember it was 1 proton and 1 electron, but now the electron's gone and it's just a proton. So an H plus is just 1 proton and it is pretty reactive, and this H plus is what makes something an acid. If we have H plus in solution, it is considered to be an acid. How we measure acidity is on the pH scale. Now pH stands for power of hydrogen, so we can see it relating to hydrogen more here. It's an inverse logarithmic scale. Inverse kind of means like backwards, and so we can see here that a low pH is a high acidity and a high pH is a low acidity, or what's called a basic, is the opposite of an acid. Now the logarithmic part is, you might have heard about it in math, but it basically means it's based off factors of 10. So a pH of 2 is 10 times different, or 10 times different concentration than one of 3. So it goes up by factors of 10, but you won't get into any of those calculations till grade 11 and 12 chemistry. Now we can see here on the pH scale below, neutral is 7 in the middle. If we are getting to the lower numbers, this is getting more and more acidic, and going to the higher numbers, this is getting more and more basic, which is the opposite of an acid and has less and less H+. Now an example of something neutral would be water. Water is completely neutral, it's not an acid or a base. But you may be thinking, if it's not an acid or a base, wouldn't that just kind of be 0? Like, why do we make neutral things and why do we make water equal to 7? Well, here's the reason. If we have a container of water, water is going to naturally break up into H plus and OH minus, just a very tiny bit. So it's making a very small amount of these H pluses. I emphasize a tiny bit there. It's not like most of water is broken into H plus and OH. It's a very, very, very small amount. The amount is actually 1.0 times 10 to the negative 7 for the concentration of these guys. That 7 is what represents pH of 7. But all you need to really know for right now is that tiny bit is equal to a pH of 7. Now as we have more water and there's more just H plus and OH, if those concentrations remain equal there of those times 10 to the negative 7, then it's going to remain neutral. That's going to be a pH of 7. But if we start to add more H pluses like we saw with the HCl, that's going to be acidic, less than 7. And the reason that is we have 1 times 10 to the negative 7 was neutral. To get a bigger number here, more H pluses, this negative exponent becomes less, like 1.0 times 10 to the negative 2. I'm not sure if you dealt with exponents that much for math, but this is a much smaller number. This times 10 to the negative 7 is 0.12345 that big of number, and this is just, 0.01, that number. So a bigger negative exponent means a smaller concentration. So now that we have more H pluses, we get closer to this number, which is a smaller negative exponent. Again, I'm going a little bit too much detail probably than you need to know. Think of just more H's, more acidic. And then the opposite is when we introduce more OHs. This makes the OH concentration higher than the H pluses, and this is going to be a base, which is going to be greater than 7. How that affects the H pluses, it actually takes some away and turns them into water, but again, you don't have to worry about that until later on in chemistry. So next, how do you determine if something is an acid or base, or determine the pH? Well, acids either begin with an H, that's the most common, or end with a COOH. Examples are HCl, you see H right at the front, because the front it's like acting like a metal or like a plus ion, and then the negative non-metal. Or H2SO4, we see the same thing there, H plus, there's two of them, and a negative SO4, 2 minus. Bases are easy to recognize because they end in OH, for example, NaOH and LiOH. Now the one that looks like it has both of these would be something if it was like CH3COOH, because you're like, okay, well that ends in COOH, but also ends in OH. When you have it ending in COOH, that is an acid. It's a carboxylic acid, which again, you learn about a little bit later on in chemistry. You will only see like one of these on a test normally. Most common, they just have an H at the start. How you determine it in real life, you can use a litmus paper, and that's what we have a diagram of here. So if it turns blue, blue means it's a base. If it turns red like this, that means it is an acid. If it stays the same color, so you put blue in a solution and it stays blue, then you put red in a solution and it stays red, that just means it's neutral, it's not an acid or a base. So it just says that here in the notes, red is acidic and you need 2 reds for red litmus paper to stay red and blue litmus paper to turn red. And then if you put red litmus paper into a base, it will turn blue, and blue litmus paper will stay blue. So you have a red and a blue piece of paper and you test that in all of the solutions if you were doing a lab to see which would be acidic and basic. Some have a specific pH, so if you get really fancy indicators, you can take that piece of paper, dip it into a solution, and it'll turn a specific color, which is matched to the pH as well. Next, we'll look at some properties of acids and bases. We'll start with acids. They are sour. You shouldn't be necessarily tasting chemicals, but some acids are actually often used in food, like citric acid is in things like oranges and lemons and limes and stuff like that. Also, vinegar is an acid as well, and that has a sour taste. It's described as being wet, which I think is a weird description, but it means like the opposite of slippery. Bases we're going to see are slippery like soaps, and it's just like not slippery like that. It is indicated by an H plus or a COOH, as we saw from before. It reacts with metal to form hydrogen gas. It's kind of a specific property, but they do sometimes ask about that. So if you put a solution with a metal and you get hydrogen gas coming off, you know that your solution was an acid. It has a pH less than 7, which we talked about, and some household examples, which I did mention, citric acid, fruits, and vinegar. Bases are pretty much the opposite of acids. They are bitter, they are slippery, they're often used in lots of cleaners. It has an OH minus, which is its characteristic group. It has no reaction with metals. Its pH is greater than 7, and some household examples are soap, like I mentioned, slippery, and baking soda. You've probably heard of putting baking soda and vinegar together in that classic acid-base reaction. So we need to know what acids and bases are, we need to know their properties, and we need to know how to name them. So we're gonna start with naming acids. So consider that hydrogen is acting like a metal. How would you name this? Well, we'd see hydrogen and then we'd see chlorine, we'd change the N to ide, and we would put hydrogen chloride. And so lots of acids are gonna look like this: hydrogen and then something at the end with a non-metal. It could be chloride, maybe it's with a sulfate, it's sulfate, maybe with a nitrite. We're gonna have another non-metal bonded to that. So what we're gonna have to kind of see here is these characteristics. The hydrogen is gonna be consistent, pretty much every acid is hydrogen bonded to something. We need to look at the end of that word. In this case, it's IDE, and the root word there is chlor, representing chlorine. So those are the 3 parts we need to recognize: hydrogen, that's an acid, the root word of the nonmetal, and the suffix at the end. Why that's going to become important is this ending determines how we're going to change this into its acidic name. So I'm going to pull up this chart that is in your data booklet that looks like this. So we can see all of your acids are going to start with hydrogen, and then we're kind of put this minus sign here, or this blank. That's where the root word of the nonmetal is going to be, and then it's either going to end in ide, ate, or ite. So for example, you could have sulfide, sulfate, or sulfite, okay? Now what you're going to turn this into is what it shows right here. If it ends with ide, you're going to put hydro, the same root word that we saw here, and then instead of just ide, ic acid. So if you had hydrogen chloride, it'd be hydrochloric ic acid. For the next one, 8 just turns to ic acid. It's the same, but there's no hydro. So if you did hydrogen sulfate, that would be sulfuric acid. So it just takes the root from here, from the sulfate, and puts sulfuric acid. And the last one, if it's ite or ite, we just take the root word of that and put ous. So if it was nitrite, you would get nitrous acid. And it does give examples over here, and you get this information on your data booklet you get to use on a test. And it's nice that it gives you some examples there of how to do it. So looking back at this example of hydrogen chloride, because it ends in ide, that's going to turn to hydro blank ic acid. We're going to use the root word chlor there to turn it to hydrochloric acid. I know that's tough to see there, but hydrochloric acid. All right, so that root word of chlor is what stays the same, and the rule for IDE is we get hydro and ic. So let's try another one. If we had HBr, that's hydrogen bromide. So bromide here makes us know that we need hydro, ic, and then we're just gonna take the root word from bromine, which is bromic. Makes bromic acid, all right? So you're just using that root word there. I know these are a little bit tough, so give them a try when you have your practice questions, and make sure you ask a lot, because this is something that usually people have some difficulty with. Now we have to name bases, so let's look at how you would normally name the following. LiOH, we would normally name that as a lithium plus, and OH is a hydroxide. You'd put lithium hydroxide, and fortunately that's it. There are no special rules for naming bases. We name them just like we used to name ionics. And so that's it for this lesson. We just know what an acid and a base are based off those H plus and OH ions. We need to know their properties, and we need to know how to get those acidic names that are in your chart. I think that's probably the hardest part of this lesson. So make sure you ask lots of questions in the live time, and I will see you in the next video.